All right, welcome back, everyone. In this part of our process control series, we're tackling a super important question. When you see a change in your process, how do you know if it's just, random noise, or if it's a real problem you actually need to fix? Well, we're going to explore exactly that, the concept of variation. And all of our insights today are drawn from the fantastic work of Mohammed Ajlouni. So, let's dive right in. So here's our game plan. First, we're going to look at the two basic kinds of variation you'll run into. Then, we'll get into the main tool for telling them apart. It's called the behavior chart. After that, we'll cover how to read the signals it gives you, how to avoid a really common mistake, a dangerous one actually, and we'll also talk about the difference between what your process is doing versus what your customer actually needs. And to wrap it all up, we'll walk through a practical example to see how it all clicks together. Okay, before we jump into new stuff, let's do a quick recap of where we left off. So, in the previous part, we established that controlling variation in process outputs requires effective control of process inputs. We also identified two primary categories of inputs, process parameters and process conditions. Building on this foundation, we introduced critical to quality, or CTQ characteristics, and emphasized the transition from inspection-based quality control to prevention through statistical process control, or SPC. Right, so basically it all comes down to this. To control the output, you gotta control the input. And we talked about moving away from just checking for defects at the end and toward preventing them using SPC. And that idea is exactly the foundation we're building on today.
All right, first things first, we have to get one fundamental idea straight. Variation is everywhere. Seriously, it's just a natural part of any process. But here's the secret. Not all variation is the same. It actually comes in two very, very different flavors.
So these are the two types we're talking about. On one hand, you've got what we call natural variation. You can think of this as the routine, unavoidable background noise of a process. It's always there. But on the other hand, you have exceptional variation. And this isn't noise at all. Nope. This is a loud, clear signal that something specific, something unusual has happened.
So that process noise we just talked about, well, it has a more formal name, common cause variation. This is the natural rhythm of your process. It's the expected, routine variation that exists when everything is stable and running the way it's supposed to. It's just part of the system. And that signal, that disruption, that's what we call special cause variation. This is the one that's caused by something identifiable, something that isn't normally part of the process. Maybe a machine part broke, or you got a new batch of raw material, or someone didn't follow the procedure. This is the kind of variation you have to investigate and fix because it's a sign that something's gone wrong. Okay, so this is the big question, right? The million-dollar question. You're looking at a chart with a squiggly line going up and down. How on earth do you tell if a little dip or a spike is just normal, everyday noise, or if it's a real signal telling you something's wrong? How do you separate the signal from the noise? Well, believe it or not, the answer lies in a tool that's both simple and incredibly powerful. It's called the process behavior chart. Think of it as our special lens, our X-ray vision for seeing what's really going on inside a process. So what does this chart actually do? Well, its main job is to define the boundaries. It uses some straightforward statistics to figure out the expected range for that normal common cause variation. It basically draws a line in the sand and says, look, this right here, this is the normal playground for this process. Anything inside is expected.
Let's break down the parts of this chart. It's pretty simple. You've got a central line right in the middle. That's just your process average. Then you have two other lines, one on top and one on the bottom. Those are your upper and lower natural tolerance limits. And if we stick with our analogy, these are basically the fences of the playground. And finally, you have all your data points, plotted over time, showing you exactly how the process has been behaving.
Now, a quick but really important note. I know what you're probably thinking. Okay, but how do you actually calculate those limits? That's a great question, and we are absolutely going to cover the methodology for calculating the limits, but that's a topic for a future video. For right now, let's just focus on how to read and interpret the chart once you have it. Okay, so we've got our chart, we've got our limits. Now for the fun part, reading the signals. What is this thing actually telling us? How do we use it to understand if our process is stable and predictable? Well, here's the ideal scenario. When you see all your data points just happily bouncing around between those two limits and you don't see any strange patterns, that's what we call a process in statistical control. And folks, this is the goal. This is what you want to see. It means your process is stable, it's consistent, and, this is the big one, it's predictable. You can actually forecast what it's going to do next. But what happens if a data point goes rogue?
What if it flies outside those limits? That is your signal. That's the chart screaming, hey, something is wrong. Your process is now out of control, and your job is to put on your detective hat. First, you identify that special, assignable cause. Then, you dig deep to find its root cause. And finally, you eliminate it, you fix it, to get the process back into its stable, predictable state.
Okay, this next point is absolutely crucial because it brings us to a really common and really dangerous mistake. Seriously, it's a trap that so many people fall into when they don't get the difference between the two types of variation. This mistake has a name. It's called tampering. And here's what it looks like. You see a normal little fluctuation in your process. A data point is a little high, the next is a little low, but it's still safely inside the control limits, and you feel like you have to do something. You react. You jump in and start tweaking knobs and making adjustments to fix it.
So why is that so bad? Because you are reacting to common cause noise as if it were a special cause signal. You're trying to fix something that isn't broken. And the irony is by making all these unnecessary little adjustments, you actually increase the overall variability. You take a perfectly stable, predictable process, and with the best of intentions, you make it unstable and you make it worse. So the number one rule here is simple. If the process is in control, leave it alone.
Okay, let's take a step back and look at the bigger picture now. Because knowing your process is stable and predictable, that's half the battle. But there's another equally important voice we need to listen to. And this is where we have to understand that there are two totally different sets of limits. On one side, you have the natural limits we've been talking about. This is the voice of the process. It's derived from your data, and it tells you what your process is currently doing. But then you have specification limits. This is the voice of the customer. This comes from their requirements, and it defines what performance is acceptable. And here's the key takeaway. These two voices are not the same, and just because you're listening to one doesn't mean you're satisfying the other. All right, I think the best way to make this stick is to walk through a quick, practical example. Let's tie all of this together. Okay, so let's say we're manufacturing a part, and the critical to quality characteristic, the CTQ, is its diameter. The customer specification says it needs to be 12 millimeters with a tolerance of plus or minus 2. Now, we go and collect our own process data. We do the math, and here's what the voice of our process tells us. Our average is 11.98 millimeters, our upper natural limit is 13.35, and our lower natural limit is 10.60. So what is this telling us? It's telling us that our process is stable, it's predictable, and under these current conditions, we can expect that roughly 99% of the parts we make will have a diameter that falls somewhere between 10.60 and 13.35 millimeters. That's what our process can deliver, day in and day out. But, and this is a really important but, notice what we've done here. At this stage, we have only been listening to the voice of the process. We understand what it's capable of. The next step, the one we haven't taken yet, is to compare that to the voice of the customer.
And that brings us to the final and most important question. Our process is stable. Great. It's predictable. Fantastic. We know exactly what it can do. But is it good enough? Is what our process can do good enough to meet what our customer needs? And that is the exact question we're going to tackle in our next session. Thanks for joining me.